What if I told you the deepest truths about our universe aren't hidden in distant galaxies, but in something, well, something kind of boring, like a handful of sand? Today, we're diving into a really wild theory that says the vacuum of space isn't empty at all. We all learn that space is this vast, empty void, right? Just nothingness. But this idea completely flips that script. It asks a simple question. What if space isn't empty? What if it's actually full of stuff? So just imagine that for a second. The vacuum isn't a void. It's a physical material, kind of like a cosmic sandbox, filled with these impossibly tiny grains all packed together as tightly as they can be. And as we're about to find out, that one simple idea, well, it leads to some really strange places. To get our heads around how this cosmic sandbox could possibly work, we're not starting in some giant particle accelerator. Nope. Our journey begins way back in 1885 with a simple wet sand bag.
Okay, so you've got a bag full of wet sand. What happens when you squeeze it? Your intuition, my intuition, says the water's going to squish out, right? I mean, that's just common sense. A scientist named Osborne Reynolds thought so too. But that's not what happened.
Incredibly, when the bag gets squeezed, the water level actually goes down. The sand pulls it in. I mean, how weird is that? This isn't just a party trick, though. It's a massive clue about how any system of packed-together stuff actually works. It's got a fancy name, Reynolds dilatancy, but the idea is pretty simple. For the individual sand grains to shift and slide past each other, they actually need to spread out a little bit. They need more room. That forces the whole system to expand, and that expansion creates a tiny vacuum that literally sucks the water in. Now here's the kicker. What if this doesn't just happen in sandbags? What if it happens on a cosmic scale? Okay, so if we run with this idea, if the vacuum of space really is just a giant system of packed grains, you have to wonder, what's holding it all together? What keeps this cosmic sandbox from just collapsing? Well, the stability of any packed system like this all comes down to how many contact points each grain has. There's what's called the isostatic limit, which is the absolute bare minimum needed to not fall apart. Think of a house of cards. But then there's the hyperstatic limit. This is where each grain has way more contacts than it needs. It's got backups for its backups. And that doesn't just make it stable, it makes it incredibly rigid and able to store a ton of energy. So where does our hypothetical vacuum fall? Well, in 3 dimensions, you only need about 6 contacts per grain to be stable. This theory suggests that the grains making up our vacuum have an average of 14.4 contacts each. That's not just stable, it's way, way into the hyperstatic zone. We're talking profoundly, almost unbelievably rigid. And this extreme rigidity, it might just offer an answer to one of the biggest mysteries in cosmology, dark energy. You know, that strange force that seems to be accelerating the expansion of our universe? In this model, it's not some exotic, mysterious field. It's just the immense elastic energy that's already stored in all those extra redundant connections in this hyperstatic vacuum.
But hang on. If the vacuum is basically a solid, that raises a whole new problem, right? How do things like light and other fundamental forces travel across billions of light years through this dense medium? Shouldn't they just get stuck?
The theory has a really cool answer. It says stress travels through this material in 2 totally different ways. Some of it gets focused into these discrete, lightning-fast channels called force chains. This is like the skeleton of reality. The theory argues that's the strong nuclear force. The rest of the stress just spreads out weakly through the rest of the material, the flesh. And that corresponds to gravity and electromagnetism. But still, if the universe is made of individual grains, how can light travel infinitely far? The answer is this thing called the jamming transition. Imagine a jar of marbles packed so tightly that they're completely stuck. They're jammed. At that point, if you poke a marble on one side, that force is felt instantly on the other side. The whole system is connected. That's how a force can have a seemingly infinite range, even in a medium made of finite parts. And this brings us right back to where we started, that weird sandbag experiment. Because this is where the theory makes its most radical claim, completely rethinking the very nature of gravity itself. So here's how it works. A huge object, like a star, deforms or shears the granular vacuum around it. And just like our sandbag, when the vacuum is sheared, it has to expand. It dilates. This expansion makes the vacuum just a little bit less dense right around the star. And what happens when light passes from a denser medium to a less dense one? It bends. We see this all the time. So what we perceive as the pull of gravity is actually just light bending as it travels through these patches of lower density vacuum. Now, this is a fundamental break with everything we know. Einstein said gravity is the curvature of space-time. This model says that's just an illusion. It's basically an optical trick, a refraction effect like a mirage on a hot day, caused by the changing density of space itself. The crazy part? The math can actually reproduce the predictions of general relativity, but the physical cause is completely different. So, what does this all mean? It's a profound shift in how we see everything. It asks us to throw out the idea of an empty, passive void and replace it with an active, structural medium that is the very fabric of our reality. Let's just quickly recap how incredible this idea is. The vacuum, it's a dense, solid material. Dark energy, that's just the stored tension in that material. The fundamental forces we see, they're just different ways that stress moves through it. In gravity, it's an optical illusion. This is a complete reimagining of the bedrock of our universe. It leaves us with a pretty fascinating final question. For centuries, we've looked to the heavens for all the answers. But if this model is anywhere close to right, maybe the deepest secrets of the cosmos have been right here at our feet, hidden in a simple handful of sand all along.